Welcome to the Strength of Materials Lab. In Strength of Materials Lab, we conduct various experiments to study critical concepts, such as bending stress, deflection, torsion, and material elasticity. These tests provide valuable insights into the properties and performance of materials under load. Welcome to this demonstration of the deflection test on a metal beam, conducted in the Strength of Materials Lab. This experiment helps us understand how beams respond to loads by measuring their vertical displacement, or deflection. The primary objectives of this test are, to analyze the behavior of the metal beam under load, measure its deflection at different points, and evaluate its elastic properties using theoretical principles. For this test, we'll use essential apparatus such as a loading frame, dial gauge, and a beam. We'll also need calibrated weights to apply controlled loads. The moment of inertia is a fundamental concept in mechanics of materials, particularly in bending analysis. It represents the resistance of a cross-sectional shape to bending or deformation under load. For a rectangular section, it plays a key role in determining how beams behave under bending stresses. For a rectangular cross-section, the moment of inertia about its neutral axis is given by the formula BD cubed divided by 12, where B is the width of the rectangle, and h is its height. This equation shows that the moment of inertia increases with the cube of the height, making the section's height a critical factor in its resistance to bending. Consider a rectangular beam with a width of 200 mm and a height of 300 mm. Using the formula, the moment of inertia about the neutral axis is, this calculation gives the value of the moment of inertia in millimeters to the fourth power. Such a large value highlights the beam's capacity to resist bending. In conclusion, understanding the moment of inertia is essential for designing and analyzing structures. For rectangular sections, the height has a significant impact, as it is raised to the third power in the formula. This emphasizes the importance of choosing appropriate dimensions for structural efficiency. The higher the moment of inertia, the greater the resistance of the beam to bending. For example, a tall and narrow rectangular section will have a much higher moment of inertia compared to a short and wide section, assuming the same cross-sectional area. The apparatus used in this experiment includes a loading frame to hold the beam securely. In the deflection test setup, the loading platform is positioned to securely hold the stones and distribute the load evenly onto the beam being tested. We begin by using weighing stones as a calibrated source of load. These stones ensure precise and uniform loading during the experiment. The magnet dial gauge is set up. This precision instrument is attached to the beam to accurately measure its deflection under the applied load. The dial gauge provides real-time, reliable readings of displacement, making it an essential tool for evaluating material behavior. Before conducting the deflection test, we begin by measuring the physical dimensions of the beam with precision. Using a measuring tape or a caliper, we carefully determine the length of the beam, ensuring we measure from end to end. Next, we measure the breadth and thickness of the beam. These two parameters are equally important as they directly influence the beam's structural properties. Next, the loading frame is fixed securely at the midspan of the metal beam. Proper alignment ensures uniform application of the load. The magnetic dial gauge is then positioned on the supports near the midspan. The dial gauge records the deflection at each step, allowing us to analyze the material's response to increasing stress. The dial gauge is attached below the beam at the midspan to record deflection. We then apply weights incrementally at the center of the beam. We prepare the magnetic dial gauge for deflection measurements. The gauge is carefully positioned on the supports near the midspan of the beam. Its magnetic base ensures a firm attachment, preventing any movement during the test. We carefully adjust the dial to set it at 0, ensuring an accurate baseline measurement. After each weight is added, the corresponding deflection reading is recorded. With the setup complete, we proceed to the loading phase of the deflection test. The load is applied incrementally, starting with the lightest weight and gradually increasing. This step-by-step process allows us to observe how the beam behaves under each specific load level. First, we place a 500-gram weight on the loading platform at the beam's midspan. As the weight settles, we use the magnet dial gauge to measure the resulting deflection. This instrument, positioned carefully at the center of the beam, provides an accurate reading of the displacement caused by the applied load. The deflection value is recorded for further analysis. Next, we increase the load by adding another 500-gram weight to the platform, bringing the total load to 1,000 grams. Again, we observe and measure the beam's deflection using the dial gauge, ensuring that the reading is precise and that all observations are carefully documented. Then, removing 500 grams, we add another 1,000 grams, bringing the total load to 1,500 grams. We observe and measure the beam's deflection using the dial gauge, ensuring that the reading is precise. We increase the load by adding another 500-gram weight to the platform, bringing the total load to 2,000 grams. This load level represents the maximum force applied during the test. As with the previous steps, the deflection is measured and recorded. Throughout this process, it's important to handle the weights carefully to ensure their placement does not disturb the beam setup. The gradual application of the load helps to identify the beam's elastic limit, if applicable, and highlights how the material responds under increasing stress. The recorded deflection values at each load step provide critical data for understanding the beam's behavior, calculating material properties, and evaluating structural performance. We can analyze the relationship between load and displacement, which is fundamental in structural engineering. As the weights are applied, the deflection is measured and recorded in a tabular format. The table includes columns for applied load, deflection readings, and any notable observations. These measurements will be used to plot a load deflection curve for further analysis. From the recorded data, we calculate the modulus of elasticity of the material using the standard formula. A graph is plotted between the applied load and the deflection to observe the beam's behavior. We start by applying incremental loads, recording the corresponding deflection values at each step. These values are then organized into a table with columns for the applied load, W, and the measured deflection delta. This data provides the basis for further calculations. The bending equation is expressed as m divided by I equals sigma divided by y equals E divided by R. Here, m is the bending moment applied to the beam, I is the moment of inertia of the beam's cross-section, sigma is the bending stress at a given point, y is the distance from the neutral axis to the point of interest, E is the modulus of elasticity, and R is the radius of curvature of the bent beam. When a point load is applied at the midspan of a simply supported beam, the maximum deflection occurs at the center. The formula for maximum deflection is given, where W is the applied point load, L is the length of the beam, E is the modulus of elasticity or Young's modulus of the material, and I is the moment of inertia of the beam's cross-section. To calculate Young's modulus E, we rearrange the deflection formula. Next, we derive the formula for bending stress using the bending equation as shown. The deflection formula helps analyze the displacement of beams under a central point load, and Young's modulus is calculated to characterize the material's stiffness. Additionally, the bending stress formula, derived from the bending equation, provides insights into stress distribution within the beam. Together, these concepts form the foundation of beam theory and structural analysis.